So we're going to look at differentiation of basic algebraic expressions. Now, differentiation is used to determine rates of change, gradient of a tangent. You can also then find the equation of the tangent, as well as stationary points and their nature. Now, a question can be asked in many different ways, and it all means the same thing. You can be asked to find the derivative, determine the slope or gradient at a given point, calculate the rate of change, which can also be at a given point, determine the slope or gradient of the tangent, find f dash of x, or determine or find dy dx. Can also just be asked, plain and simply, to differentiate the function. Every single one of those mean exactly the same thing. And how do you go about doing it? Well, you simply multiply each exponent by that term's coefficient, and then you subtract 1 from the exponent, which is shown here as Leibniz notation. So that's the dy dx notation, and your normal equation would have started with a y equals whatever your function is, as well as this notation here, which is Lagrange notation. They're both the same, they just look a little bit different, both done exactly the same way, so let's have a look at how that's done. Okay, so number 1 asks me to find dy dx, so it's just asking me to differentiate. So each term, look at each term separately. We bring the exponent to the front and multiply it by the coefficient. So negative 1 times 3 is negative 3. Then we put the variable back where it was, and we reduce the power by 1. So that becomes 2. Then we repeat. So the next one, it's going to be 2 times 8, which is 16. Put the x in, and then reduce this 2 by 1. Now you don't have to put a 1 there, because anything without a power automatically is to the power of 1, but you can if it helps you. The negative 20x is the last term we're going to do, because as you can see, this power is 1, so 1 times negative 20 is negative 20. And if I reduce this 1, I get 0, and x to the power of 0, or anything to the power of 0, just equals 1, so it disappears. And this term has no variable, so it's going to disappear completely. So this is your final answer, or dy dx, if you're going to write the full notation, is equal to negative 3x squared plus 16x minus 20. Now part 2 asks us to determine the gradient of the tangent at x equals 1. Now the gradient of the tangent is exactly the same thing as finding the derivative, or differentiating. So when we differentiate, we are literally finding the slope at any given point of the function. So I already have worked that out, so all I need to do is substitute x equals 1 into the function that I now have. So I have negative 3 times 1 squared plus 16 times 1 minus 20. So all I did there was made for x equals 1, put 1 wherever x was, plug it in, and now I'll solve it. So 1 squared is 1, so I just get negative 3. 16 times 1, well, that's 16, minus 20. Negative 3 plus 16 is positive 13, minus 20 is negative 7. So the gradient of the tangent at x equals 1 of this original function is negative 7. The only thing you really need to be aware of when doing these basic algebraic expressions is that you cannot have fractional or negative exponents in your answer if you're asked for rate of change, slope, or gradient. So let's go ahead and work this one out. So 2/5, got to multiply that by 6, so we get 12 over 5, and we still have to reduce this by 1. So it ends up being negative 3/5. Because 2/5 minus 1 is negative 3 over 5. Now this is a negative exponent. It's also fractional, so we can't have that. So we need to think back to our index laws, which I've put the 2 we need over here, so that we can rewrite that exact same expression with a positive exponent and without the fraction. To make it a positive exponent, we simply drop it from the numerator to the denominator. So we end up with 12 over 5. X to the positive 3 on 5. So we've now made it positive, but we still need to get rid of that fraction. So now we're going to have a look at this other index law and apply it. So So the 12 is going to stay where it is. The 5 is going to stay where it is. And then we just need to copy our index law if you can't remember it. So the n is the number down the bottom, and that goes out the front of the radical. So in ours, that is a 5. So it's a fifth root of x. M is the number on the top, and that goes inside our radical, and that is a 3. So this answer here is exactly the same as this one, but written in correct form, which enables you to substitute a value of x if needed without the use of a calculator. Because remember, you're always going to have a paper that has 0 calculator usage. So in this form, it's much easier to substitute a value than it is in the original form you had.